asteroid and return a sample to Earth. Bennu is a dark, diminutive world, roughly the height of a skyscraper, and now the smallest body to be orbited by a spacecraft. Prior to arrival, it was known to have low thermal inertia, a characteristic of fine-grained materials like sand.
So we landed on Bennu, yes.
On Osiris-Rex confirmed this property, leading scientists to expect
Wait
a
till you see the
predominantly
surface of
smooth
this
surface. But the first close-up views of Bennu delivered a major surprise. In exquisite detail, the mission's cameras revealed an unrelenting rockscape dominated by boulders. By combining these images from Osiris-Rex with its laser altimetry data, we can take a tour of Bennu's remarkable terrain. The first stop is Simurgh-Saxum. This prominent boulder defines the asteroid's prime meridian and serves as the basis of its coordinate system. In Persian mythology, the Simurgh is a large and benevolent bird and the possessor of all knowledge. Saxum is Latin for stone. To the northeast lies the largest boulder on Bennu. Measuring over 300 feet in length, Rock Saxum is a colossus longer than a football field. It is also rich in a type of iron oxide called magnetite, which was used by mariners as an early form of magnetic compass. In Arab folklore, the rock is an enormous bird of prey that can clasp elephants in its talons, as well as stranded sailors like the hero Sinbad. Continuing northeast over the equatorial ridge, we arrive at Gargoyle Saxum. This striking boulder is among the darkest on Bennu, though it clutches a much brighter rock that is about the size of a person. In medieval legend, gargoyles are dragon-like, winged monsters that can breathe fire and that guard cathedrals from evil spirits. Our next destination takes us far to the east. At the northern end of a small crater lies Ocypete Saxum, a comparatively bright boulder measuring about 33 feet in diameter. Ocypete Saxum is located near one of 3 sites where Bennu ejected small particles into space in early 2019, displaying its dynamic and evolving nature. In Greek mythology, Ocypete is one of the 3 harpies, the half-maiden, half-bird personifications of storm winds, who would carry evildoers away from the earth. In the creation stories of ancient Egypt, the universe began as a formless, endless expanse of water. From this primordial sea arose the primordial mound, Benben. It was upon this rock that the god Atum settled in the form of the Bennu bird and sent forth the call that shaped creation. The story of Benben harkens to the mounds of fertile silt that once emerged from the receding floodwaters of the Nile, and it provides a fitting namesake for the tallest boulder on Bennu. Protruding by over 70 feet, Benben Saxum is so tall that it was first detected from Earth. Now, we can appreciate this monumental feature in detail using data from Osiris-Rex. The final stop on our tour is a cluster of exceptionally bright boulders scattered across the southern hemisphere. They bear the spectral fingerprint of pyroxene, a mineral found in igneous rock that is unlikely to have formed on Bennu. These boulders most likely originated on the large asteroid Vesta and were delivered to Bennu's parent body through meteoroid impacts. Although it is small in size, asteroid Bennu has proved to be a fascinating world, abundant in geographic features that have defied our expectations. Thanks to Osiris-Rex, we can now explore Bennu to uncover its composition, its evolution, and its ancient memories from the origins of the solar system.
So can anybody tell me in chat why we study Bennu in particular? There's 2 reasons, really. Well, I'll tell you the first reason. The first reason is that our planet was formed about 4.5 billion years ago, and the stuff that formed our planet was incredibly modified and morphed into other chemicals, other minerals, other things like that. So we really don't know what the original rocks that formed the universe, formed the solar system are. However, Bennu is essentially primordial. The rocks that are on it are from the original creation of the solar system. And that tells us a lot about the creation of our solar system and the creation of other solar systems. So that's reason number one. Reason number two, it's on a collision course for Earth. So in 2175, there's a non-zero % chance that it will hit Earth. And although it won't, make the dinosaurs go extinct, if Bennu hit a city, that city would disappear. It's several thousand megatons of potential explosion. So understanding Bennu is a real good thing. So for example, if we hit Bennu now with some sort of explosive, would it change its orbit, or it would just shatter into a quintillion pieces? We need to know these things. I like the fact that we're trying to protect the Earth that is hundreds of years from now, or 150 years from now. So, our future generations, we're not considering our own lives here. Anyway, that's Bennu. Let me bring up just another reminder. The most important thing you can do this year is vote. This is without a doubt the most influential, important election since the founding of the country, actually, since 1787. Now that was an election. This one is just as important. So do whatever you can to vote. Do whatever you can to help other people vote, because you're going to be living in this world much longer than I am. So pack the polls, just do the web search for this. We'll tell you everything you need to know. Let's see. Also, we have an exam coming up. Today is October 22nd. We're in lecture 19. Next week, we've got a lecture on Tuesday, and then we have an exam on Thursday. The exam is exactly like previous exams, actually like exam 2, where it opens up at 10:15, closes at 11:30. You have 75 minutes to do the exam. There's 79 questions on it. They're multiple choice, true, false, fill in the blank. Any questions about the exam? And so remember, your class presentations are due November 12th. I will show the best of the lot on November 17th. So hopefully that'll be a fun lecture. And you get full credit if you turn in something. You get extra credit if you turn in something that's really good. So I'm not going to give you A, B, C, D on the project. I want you to have fun with it. I'm not going to grade it, other than the fact that the good ones I will give extra credit to. And so exam 3 covers chapters 13 through 17. Let me show you that. And I just posted yesterday the guide for this exam. Is the final cumulative? Absolutely, it is cumulative. So Frank, actually, I think this is more important than the election in 1968. So here, these are the topics that will be covered in the exam. So exam 13 through, chapters 13 through 17. Okay. Oh, yeah. And so this is posted under resources on WebSign, as is all the lectures now that I have, all the lectures from the publisher, plus a bunch of files such as these exam guides, such as the formula file and the syllabus. So that's it. And let's get today's lecture. It'll be a fun one. Of course, they're all fun, aren't they? I mean, astronomy, imagine if we were doing linear algebra, that would be less fun. But astronomy, gosh, who doesn't love astronomy? So today we're going to be talking about dark matter, and if we have time, we'll be talking about galactic collisions. We probably won't, and we'll drift that over to Tuesday. So I'll give you a brief review of what we covered last time, the Hubble expansion and the distance ladder. And then we're going to spend a lot of time talking about dark matter, okay? So dark matter is something that beginning in the 1970s, we understood that there was something wrong with our knowledge of the location of matter in the universe. And it's just in the last 20 years that understanding that we really don't understand things, you get it, has really accelerated. And we're now at the point where we believe that there's 10 times more mass in dark matter than there is normal matter. And we have no clue what dark matter is. We just know that it's gravitational, it is mass, but we don't know anything else. We don't know it's particles, is it a field, is it gargoyles, is it black holes? We just don't know. So today we're going to be covering 4 of the 7 lines of evidence for dark matter. At the end of this course, you will be absolutely positively convinced dark matter exists, even though you can't see it, okay? There's something that permeates the universe that does not interact with you. In fact, you are looking through dark matter right now, presumably. You're surrounded by dark matter. Dark matter is inside you, and you have no way of perceiving it. And then if we have time, like I said, we'll talk about galactic collisions and mergers. The Andromeda Galaxy is on a collision course for our galaxy, and in 4 billion years,
hey,
it will collide.
Brand, you didn't turn on the PowerPoint.
Oh my gosh. Thank you so much.
It's okay.
Oh boy. Okay, thank you. Thanks, Ward.
Yeah, it's okay.
I really enjoyed my linear algebra class. Yes. Thanks, Jen. I didn't mean to. I was just picking something out of the hat. I actually like linear algebra too. I can't believe I did that. Even the best was making it. That's the first mistake I've made all semester, isn't it? Okay. So we'll talk about dark matter, evidence for dark matter. Ward, thanks for turning on your mic. I wasn't paying attention to the chat like I should. Gravitational lensing and galactic collisions and mergers. This picture here shows a collision between our galaxy and the Andromeda Galaxy. The Andromeda Galaxy is on a collision course for our galaxy, and in 4 billion years, those 2 galaxies are going to collide. And the question is, what does that do to us? So, refresher on Hubble's law. What we discovered is the farther away galaxies are from us, the faster they're moving away from us, which makes sense if the entire universe is expanding. And we covered last time that there's no center of that expansion. We're just a big bubble and everything is expanding. And Brody, I really appreciate that. You're right. I'm perfect. That's what everybody tells me. So Hubble's law, this is a fundamental law of the universe. And this constant is the most important number, I believe, in all of science. And that tells us how fast the universe is expanding. If the universe is expanding slowly, then the universe is old. If the universe is expanding rapidly, then the universe is young. And the expansion of the universe also tells us whether the universe will stop and recollapse or the universe will continue to expand forever, whether we die in fire or ice. We'll be covering that in future lectures. And here, remember the distance ladders. They're the different ways we measure distances. We use Kepler's laws close up. We use parallax for nearby stars. We use main sequence fitting. We also call that a spectral parallax to find stars that are reasonably far away. And then within our galaxy and nearby galaxies, we can Cepheus variables and then type 1 supernova. So let's bring up the first poll. So how would you get the distances to the nearest galaxies if you megaparsecs? A, parallax, B, Cepheids, C, Hubble's law, D, radar reflection, E, main sequence fitting. Okay, most of you chose Hubble's law. The thing is, Hubble's law is the result of these distance calculations. It's not how we get the distance calculations. We use these distances to calculate the Hubble constant, which is the most important constant. I mean, sure, if we assume a Hubble constant, then we can assume a distance, but it's kind of reversing cause and effect here. So really the answer is B, okay? So if we go back to that slide, Milky Way and nearby galaxies Cepheid variables. And yes, you will be responsible for this, that these are the different ways that we do distances for the exam, okay? You see a, stop sharing, sorry. You see a distant car in the night. What 2 things must you know in order to estimate its distance? A, how fast it's moving away from you. B, its apparent brightness. C, its intrinsic brightness, D, A and B, E, B and C. Okay. You really have to get this right. What does the Doppler shift have to do with brightness? In the chat, or you can turn on your mic. What does the Doppler shift have to do with brightness of the star? Nothing. Sam, that's exactly right. It has nothing to do with the brightness of the star. So you see a distant car at night. What two things must you know? So I'm going to redo this because you really need to know that. You really need to get this one right. And very good. The answer is B and C. If I know how bright something appears and how bright it really is, that will give me the distance. So remember, the flux, which is how bright it appears, varies as 1 over the distance squared. So if I go down 1/4 of the flux, then it's 2 times this distance, 1 over the distance squared. So every time I go for a factor of 2 distant, I've got, 1 over a factor of 1/4 drop in luminosity. So if I know the ratio of the apparent brightness to the intrinsic brightness, how bright it really is, that tells me the distance. Brightness equals luminosity over distance squared. Okay. And you really need to know that. So you see a main sequence B-type star like Rigel in a distant galaxy. What two things you need to know in order to estimate its distance? A, how fast it's moving towards you. B, its apparent brightness. C, its intrinsic brightness. There's actually 2 good answers to this, and we'll talk about that. So if this was an exam question, I would give credit for 2 answers. Five, 4, 3, 2, 1. Okay, so this question is similar to the previous question. And so if we know the apparent brightness and the intrinsic brightness, then we can know. So the answer is E. However, I would also give credit to the answer B, because the fact that it says it's a B-type star, if it's on the main sequence and it's B-type, I know exactly how bright it is. Okay. And so I don't need to, so I already know that. So I would also give credit for B. And there's Rigel, again, because it's on the main sequence, we know exactly what its brightness, what its intrinsic luminosity is. And we know we know it's on the main sequence and we know its color, then we know where it is on the main sequence, and that tells us. I mean, the HR diagram and the main sequence is just an incredibly powerful tool. Okay, last question before we launch into the new material. What do you need to know in order to estimate the distance of galaxies where you can no longer see individual stars? 5, 4, 3, 2, 1. Okay, this is something you really need to know. The correct answer is supernova. If you can no longer see stars, then you can't use Cepheids, because Cepheids are individual stars. If you no longer can see stars, then you can't do main sequence fitting, because that requires stars. You clearly can't use parallaxes. That only works out to the closest stars. And the type 1 supernova, the supernova that was carbon detonation supernova, where you have a white dwarf, they're all the same intrinsic brightness, intrinsic luminosity, and they're the same luminosity because they're all 1.4 solar mass white dwarfs that are imploding, because they all hit the Chandrasekhar mass at exactly the same mass. And so the fact that we know that all type 1 supernovas, the book says type 1A, type 1A supernovas are exactly the same luminosity, means if we know how bright it appears, I can tell you how far away it is. And that fact on the type 1 supernova was the genesis of the greatest scientific discovery of the 20th century, which happened in 1999, almost the end of the century. And we'll be talking about that in a future lecture. Okay. So again, the type 1A supernova, where it hits the Chandrasekhar mass. Okay, so what is dark matter? We first discovered dark matter in the 1970s, and we've shown you this slide before when we were looking at the rotation of the sun around the Milky Way galaxy and the speed that stars go around the center of our galaxy should have followed this blue line. This blue line is the farther away you are from all the mass, the slower you're going to go around, which is exactly what happens in the solar system. But instead, we measure the velocities of stars farther out reaches of the Milky Way galaxy, and we get this line here, which implied that almost all the mass is not in the center of the Milky Way galaxy, which is the way it appears. If you count the stars, they're all in the galactic core here. There's very few in the disk, relatively speaking. And so that's why we would have this. But instead, we find this. So we knew even in the 1970s that something was screwy. Okay, and here's the orbital equation if all the mass is concentrated towards the center on the square root of GM. So it's 1 over the square root of R, and the speed should diminish, but it doesn't, which implies that there's more mass outside the Milky Way galaxy than there is inside. In other words, there's mass around the Milky Way galaxy we can't see. Okay, so we started to call that dark matter. But frankly, nobody really believed it because it was just too extreme of a theory. Well, we now know that it's not an extreme, well, it might be an extreme theory, but it is the way the universe is built. So before we go farther, we should compare dark matter to the force, okay? Well, the force is what gives a Jedi his power. It's an energy field created by all living things. It surrounds us and penetrates us. It binds the galaxy together, okay? Well, there's some connections with dark matter and the force. First of all, forces, as far as we know, dark matter does not give Jedis their power. At least we don't think so. We don't have any evidence for that. Is dark matter an energy field? We frankly do not know. It might very well be, okay? And there's lots of theories that say it is. Probably not created by living things. Dark matter surrounds us, absolutely. It penetrates us, absolutely. Dark matter is spewing through you right now, and it definitely binds the galaxy together. So if you think of dark matter as the force, you're not that far wrong, okay? So how does dark matter, I'm going to give you the punchline before I give you the evidence for dark matter. Ordinary matter has mass, okay? Ordinary matter is stars and galaxies and dust and you, okay? You are ordinary matter. And we detect ordinary matter through electromagnetic radiation and more recently through gravitational waves. So when normal matter interacts with normal matter, it generates electromagnetic radiation, and we observe that electromagnetic radiation. Dark matter, on the other side, it also has mass. And I'll tell you in a few minutes why we know that. Dark matter does not interact with electromagnetic radiation. That means it's completely transparent for all forms of electromagnetic radiation. So for example, you're looking through glasses or you're looking through a window and you say they're transparent. Well, yes and no. They're transparent to visible light, but they're opaque to other forms of electromagnetic radiation. Dark matter is transparent to all forms of electromagnetic radiation. And as far as we know, it doesn't interact with electromagnetic radiation and it does not interact with matter. So it can pass through you and you don't know. Okay. So how on earth can we say anything about it if it doesn't interact with matter and it doesn't interact with light? It does interact gravitationally, though. It attracts things gravitationally. You can orbit dark matter, okay? And we believe that 85% of the matter in the universe is dark matter, something we cannot observe other than through its gravitational effects on other objects. So this is a big, big mystery. Brand has harnessed the power of dark matter for the purpose of universe domination. That's not a bad plot line, okay? Just imagine Darth Vader with the power of dark matter. Yes. Okay. So, dark matter explained.
Have you ever had the feeling that there's something bigger out there, something you can't see? Well, there is. It's called dark matter. Dark matter is spread throughout space, engulfing the Milky Way and all other galaxies. It's 4 times more common in the universe than visible matter, yet we've never seen or directly observed it. So how do we know it's there? Because of gravity. A galaxy is like a giant merry-go-round that all the stars are riding. In order to stay on, each star has to hold on tight. That's where gravity comes in. Otherwise, it'll fly off into space. The problem is, the force of gravity from all the stars we can see isn't strong enough to hold galaxies together. All the stars should be flying off the edge of the merry-go-round, but they're not. It's as if some invisible rope is helping them hold on. Physicists believe that rope is the gravitational force from stuff we can't see, hence dark matter. And how do we know the speeds of stars in distant galaxies? The Doppler effect, which is why a police siren shifts to a lower pitch as the car passes, also works for light. That's how radar catches you speeding, and how astronomers measure the rotation of galaxies. So, we use what we can see to tell us about what we can't.
And there's a lot more about dark matter. So here are there's actually more, but here are the 7 lines of evidence I'll be talking about for dark matter in this course. Galactic rotation curves, galaxy clusters, the bullet cluster, gravitational lensing, Big Bang nucleosynthesis, cosmic microwave background, and large-scale structure of the universe. I'll be talking about the first 4 today, and the last 3 I'll be talking about in future lectures. And hopefully you'll be absolutely convinced there's something very mysterious about this. And dark matter is probably the number 2 most mysterious thing about the universe. Number 1, we'll wait for a future lecture. It is the most mysterious and awe-inspiring mystery that faces us today. So galactic rotation curves, we've covered this a few times. I'm going to go into a little bit more detail here. Here, if you're rotating, a sphere, such as a Frisbee that my daughter gave me to Dad. This is Tufts University. So this rotates, and the speed of the rotation at the edge increases the farther out you're away. And that's true with a merry-go-round, okay? Keplerian motion is the speed of that rotation as you get farther away from the sun. And so the farther away you get from the sun, not only does it take longer to get around because the orbits are much bigger, but the speed is very slow. So Pluto is going around our sun much, much slower, at a much, much slower speed than the Earth does. And that's just because the square root of 1 over GM over R, okay? And so here is a little video of our solar system. You see Mercury, Venus, Earth are spinning around. The outer planets are moving very, very slowly. Okay. And there is the Keplerian rotation curve for the planets in our solar system. And here is what the galactic rotation curve is. And on the disk, it's basically flat. So this is what it looks like. So it still takes longer the farther you are out because the orbit is much bigger. But on the left is the Keplerian rotation, and on the right is the rotation that we see in our galaxy. Okay. And if you actually look, although it looks like these are going faster, they're not, because they're just, the orbit is just that much smaller. Okay. And this has been a big mystery for 50 years. We now believe that mystery is because here is our galaxy. This is actually the Andromeda galaxy, but our galaxy looks very similar to that. And our galaxy is surrounded by a sphere of, we believe, dark matter. And this sphere of dark matter has 4 to 5 times the mass of the matter that we can see. And we see, again, here is this rotation curve. We can measure this rotation curve for other galaxies by just looking at the Doppler shift of one side of the galaxy versus the other. And so here we see the red shift and the blue shift relative to the center of this galaxy. And as we look in other galaxies, to a greater or lesser extent, all galaxies have this flat rotation curve, and almost all galaxies. I think we found a couple that don't. But for the most part, we believe that most galaxies in the universe have these dark matter halos of dark matter that surrounds and permeates them, and that has 5 to 10 times more mass than the galaxy itself. Okay, I love this cartoon. Anyway, haha. Is it possible that instead of this being some new kind of matter, it's just our equations for gravity are again incomplete? Art, that's a very good question. There are many, I wouldn't say many, but there are several astrophysicists who actually believe exactly that. They call that modified Newtonian mechanics, MOND, modification of Newtonian dynamics, MOD, yes. The problem is that there's been lots of experimental tests or observational tests of MOD, and it's not done too well. And unfortunately, I don't know the details. But because we have no idea what dark matter is, theorists have been jumping in with both feet. And there's probably several dozen potential theories for dark matter. Are they particles? Are they big particles? Are they little particles? I know just in the last few months, people have been talking about small black holes. There's also talk about a fifth force. Okay, that would do it. Can we detect gravitational dark matter effects on a smaller scale? Is Earth more massive than it seems like it ought to be? So Sam, that's a good question. For the most part, the answer is no. I do know that there are some experiments that are trying to detect differences in the gravitational force in our solar system. The problem is that it's really touchy because, we know where most of the mass of the solar system is, but there's a lot of mass we don't know, a lot of asteroids and things like that. And if we're off by, a few percent on a tally of normal matter in the solar system, that could affect our observations. So for the most part, people try and do observations looking for dark matter in much larger regions, usually, the size of galaxies or clusters of galaxies. Okay, so the galactic rotation curves we mentioned several times, that's pretty straightforward. We next have galaxy clusters. So as we'll talk about in future lectures, galaxies like to be among other galaxies. They're kind of like people. And galaxies tend to cluster together into clusters in what we call superclusters. As if I showed you last time, you could kind of see that clustering. And the problem is that these clusters shouldn't exist. They shouldn't exist because galaxies are moving very quickly relative to each other. And so these clusters should dissipate very quickly, and they don't. And so the fact that clusters exist mean there must be something holding these clusters together. And the only thing that could hold these clusters together is lots and lots of mass that we do not see. And so we see these galaxies moving very, very quickly, but they stay together, which means they must be moving very, very quickly around a large central mass that is invisible to us. That's line of evidence number 2. Now, I said there's 7 lines of evidence. Some of these you can think of other explanations for it, and the galaxy cluster explanation is a bit statistical. Okay. But the fact that we have so many lines of evidence really kind of puts the nail in the coffin of people that say dark matter doesn't exist. It does exist. We just don't know what it is. We don't know if it's, as Art says, that's a modification of our laws of nature. Is it a different force? Is it a different type of matter? So a really, really strong line of evidence is what's known as the bullet cluster. This is an observation of a single galactic collision. So here we've got 2 galaxies that collided. And what you're seeing, I'll be talking a lot more about this picture shortly. And what you're seeing is this blue and this red, and the blue and red are separated. The blue represents the distribution of mass that we calculated through gravitational lensing. The red represents the distribution of matter that we mapped through X-ray emission. Okay. So here we're going to talk about collisions. So when regular matter collides, it collides and it creates something different. So if you and a fellow student run into each other, what you're going to wind up with is a mess. In other words, the 2 students do not pass through each other. Or, you throw 2 lumps of Play-Doh against each other, you get one big lump of Play-Doh plus a sound. Okay. Can we detect, is Earth more massive than it seems to be? Super duper massive black holes. Yes. So dark matter, what dark matter does, and we believe that dark matter, not only does it not interact with electromagnetism and matter, it doesn't even interact with itself. Okay. So dark matter just passes through itself. Okay. And if that's true, and we have a lot of evidence to suggest that is true, then we have this, what's known as this bullet cluster. Here is the optical in X-ray, and here is the dark matter, again mapped through gravitational lensing. Okay, and what we think happens is these 2 galaxies collide, and the normal matter kind of sticks around. The normal matter, their speed has been slowed down because they collided and they interact with each other. The dark matter, which is represented by the blue, just sails past each other. And so the fact that the location of the matter, and the matter that we observe through gravitational lensing and the matter we observe through X-ray emission are in different locations is very, very strong evidence that dark matter exists, and dark matter does not interact not only with normal matter, but with itself. Okay, that's line of evidence number 3. Line of evidence number 4, which we used for line of evidence number 3, is called gravitational lensing. If you remember when we talked about general relativity, what we said is that general relativity means that mass warps space-time. If space-time itself is warped, then gravity works on everything, not just matter, but on light and neutrinos, everything. Okay. And so that means if you have something that's really massive, light itself will be bent by that mass. It's called gravitational lensing. And this is yet another effect that Einstein said his equations predicted, but he didn't think it could ever be observed. Boy, was he wrong. Okay. In fact, gravitational lensing so permeates the universe that it's almost an irritation. So first I'm going to show you a visualization if a black hole visits Baltimore, where I used to live.
This scientific visualization demonstrates the visual distortion known as gravitational lensing. A black hole with roughly the mass of Saturn is imagined to pass over the inner harbor in Baltimore, Maryland. The view of the buildings on the far side of the harbor are distorted using the calculated effects of Einstein's general relativity. A black hole warps the space around it. Light that passes near a black hole will follow curved paths and can create multiple images and other visual artifacts. Note that the sky can sometimes be seen by looking below the black hole. These distortions are similar to what can be produced using glass lenses and are produced by similar optics equations. The effects are called gravitational lensing, lensing that redirects light using mass instead of glass.
So this was, so again, we're just using mass the same way that lenses bend light, except here it's mass that bends light. And that fact that when they talked about how you can see the sky below instead of above, that's very similar when we looked at the picture of the black hole, and especially in the movie Interstellar, where it was higher resolution. What you were seeing wasn't the black hole with its accretion disk as it really appears. Well, we're seeing it as it appears to us, but that image was created by the extreme gravitational lensing of the black hole itself. And so we were actually seeing the backside of that accretion disk bent forward towards us, just as you saw in that simulation about Baltimore. So here are some pictures that we've taken of various galaxies in the universe. And look at these arcs. Those arcs are known as Einstein's arcs or Einstein rings. Okay, and this is kind of a perfect ring. And what these arcs are the images of galaxies that have been strongly distorted by foreground galaxies. And here you can actually see that the background galaxy is probably immediately behind this foreground galaxy. And the lensing effect of gravity has actually warped that image so it almost completely surrounds this other one. Okay, and this is what I mean by this warping just pollutes a lot of images that we see. It happens all over the place. So Einstein would have been just confounded about how common this sort of gravitational lensing is. Okay, so we can use this gravitational lensing then to map mass, not only normal mass, but dark matter mass. Okay, and I love this one. Kind of looks like a smiley face. Okay. And so what you're going to see is a simulation. And the simulation is first where you see a cluster of stars that have been warped by what we think is the distribution of dark matter in the galaxy. And you're going to see how the images are warped through gravitational lensing. And then midway through this simulation, we're going to remove the dark matter from the simulation and watch what happens. And not only would the gravitational lensing go away, but the gravitational binding of the cluster disappears too. So here you see the cluster of galaxies is bound. They're all orbiting each other. And the images of galaxies behind them are warped by the amount of mass in that cluster. And now we just got rid of dark matter, okay? And we no longer have that gravitational lensing and the cluster dissipates. Okay. The thing is, we see so much gravitational lensing that we must have dark matter. Okay. Without dark matter, we wouldn't have anywhere near the amount of gravitational lensing we have if all the matter that existed was matter that we could see. Okay. I'm still confused about how galaxies and galaxy clusters don't just consume each other. Unlike revolving around, galaxies are revolving around a black hole. If the black hole can distort space-time, how have galaxies not collided billions of years ago? So Douglas, galaxies collide all the time. I mean, literally all the time. In fact, our galaxy has the remnants of probably 24 collisions. And we'll be talking about that if we have time today. And if we don't, then we'll talk about that next Tuesday. Okay. And that's the big thing. So stars almost never collide because stars are millions to billions times farther away from each other than their respective radii. Galaxies are like 10 galactic radio away. Okay, so the Andromeda galaxy is about 1 million light years away, and both galaxies are 100,000 light years across. That's a factor of 10 to 1 versus 100 million to 1. So galaxies are always colliding, and we believe that the black holes at the center of these galaxies also collide. Now, remember, even though our the black hole at the center of our galaxy is 4 million solar masses, even a 4 million solar mass black hole is still microscopic on the scale of the galaxy itself. So the the black hole at the center of our universe is about the size of the orbit of Mercury, I believe. Okay, so we're talking about something that's a few light seconds across. So light seconds compared to 100,000 light years. So since there's about 3 times 10 to the 7 seconds in a year, that would be 10 to the 7, 8, 9, 10, 11, 12, about 12 orders of magnitude difference in the size of the black hole at the center of the Milky Way galaxy to the size of the galaxy itself. That would be like a paramecium compared to the size of Raleigh. Okay. So, so those are the 4 lines of evidence that we'll talk about today's lecture. There's 3 others. So there's galactic rotation curves, galaxy clusters, the bullet cluster, gravitational lensing. And then in future lectures, we'll talk about Big Bang nucleosynthesis. The creation of elements in the Big Bang makes no sense if the Big Bang did not include dark matter. We wouldn't be here if dark matter didn't clump up matter to form the galaxies and stars that we have grown to know and love. And the structure of the universe that we observe would be radically different than what we observe if it wasn't for dark matter. Okay, so another 3 lines of evidence we'll be talking about in future lectures. And we'll end dark matter with the dark matter rap.
No Skills Entertainment. Space stuff. Dark matter.
Look up in the sky, there's the moon you see. There's some stars, there goes Mars, Pluto, R.I.P. Those are just a few of the things in our galaxy. All of it's held together by tons of gravity. But what if gravity wasn't strong enough? Everything in the universe is held by some other stuff. Some other stuff you cannot see with the naked eye. Some other stuff that doesn't shine when it's hit with light. It seems that we have ourselves another mystery. So let's travel back in time to 1933. Fritz Zwicky was observing the coma clusters, and this would lead to an astronomy adjuster. He was measuring those galaxies' mass, and based on the observed mass, they were moving way too fast. There had to be something else to cause such speeds. Apparently, we had missing matter missing from the galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see. Oblivious to dark matter
Alex.
in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see. Oblivious to dark matter in our galaxy. The center of our solar system is the sun. The closer that you get to it, the stronger gravity becomes. Close planets revolve fast, far planets slow. It's the gravity to distance to speed ratio. So if the coma clusters are moving too rapidly, maybe something invisible added to its gravity. Decades later, based on further observations, dark matter is a name of the situation. Well, what is it? No one knows for sure. An accurate description remains unsecured. Search for answers activated, simple yet complicated, constantly investigated, mysteries generated. Matter or a particle, guesses hypothetical, research problematical, and others very skeptical. But for now, that's just how the story goes. It's a known unknown, a thing we know but just don't know. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see. Oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see. Oblivious to dark matter in our galaxy. There's a lot of concern with the dark matter case, as it may be 80% of the stuff in space. Holding the stars together like some cosmic paste. Scientists are in a rush of proof. Space race. Let's talk about some of the theories that have generated dark matter, maybe how our universe originated. Following the Big Bang, the universe formed after, and it may have come together with the help of dark matter. String theory mentions dimensional planes, stacked on top each other like some video games. There's universes above us, but we cannot see them. Dark matter may be the gravity that's in between them. So if you're in a quest for the dark matter reward, you'll have to explore 11 dimensions or even more. Now I understand if that is hard to believe. The universe is like bread and dark matter is the cheese. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see. Oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see. Oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see. Or maybe we just don't understand gravity. Maybe you're right about that.
Yeah, and so it's a little weird because usually when you teach a course, you teach what we know. Here, I'm actually literally teaching what we don't know. And that teaching what we don't know is going to accelerate as we get farther in this course. Galactic collisions and mergers. Like I said, galaxies are very, very close together. Here's a picture, and this is actually to scale. There's the Milky Way galaxy, and those are the actual sizes of these other smaller galaxies relative to the Milky Way galaxy. And there's the Andromeda galaxy, and it's about 10-to-1 ratio. So galaxies are relatively close to each other.
Looking deep.
What I'm going to show you here, I have two things about galactic collision. The first is how galaxies were first born. Galaxies were first born through collisions, and then I'll show you some videos about the way galaxies are colliding today.
Looking deep is looking back. Back to when the universe was younger. Right now, our best tool for viewing the young universe is the Hubble Space Telescope.
This is Hubble's deepest view into space, known as the Hubble Ultra Deep Field. Here, astronomers have found galaxies so far away that their light began its journey to us more than 13 billion years ago.
We're seeing these galaxies as they were when the universe was just 600 million years old.
In human terms, this discovery is comparable to a teenager looking at a 6-month-old baby.
But for these galaxies, the universe was no nursery. It was more like a brutal football game.
The earliest galaxies were small dwarfs, smaller even than the ones Hubble has seen. They grew by colliding and merging with other small galaxies, as shown in this simulation.
Over billions of years, these mergers built up the giant galaxies we see today. Mergers triggered pulses of star formation that created the elements necessary for planets, and ultimately, life. But to see beyond Hubble, to witness the origin and development of galaxies, astronomers need a new tool. This is Hubble's successor, the James Webb Space Telescope, which is now being built.
Its mirror, 2.75 times the size of Hubble's, and instruments are optimized for a part of the spectrum where the most distant galaxies shine, the infrared. Hubble sees infant galaxies.
The James Webb Space Telescope will see newborns.
And the next video is going to show you a single galaxy, the birth of a single galaxy in some detail. And you can see how we got all these irregular galaxies slamming into it. I mean, it's just a big demolition derby. But then as the galaxy gets bigger, you know, it starts to form into something that we can recognize. Thank God we got powerful computers that can do this stuff. We didn't when I was a graduate student. So bigger and fancier, but it'll make cool desktop wallpapers. Absolutely. I mean, we're beginning to see a spiral galaxy that we would be familiar with. And these simulations include star formation and the shock waves that happen when gas clouds collide. And here we have a nice spiral, actually a barred spiral galaxy, just like ours. It just kind of forms organically out of the process. So colliding and merging galaxies, they dominate the history. Here is a graph of what we think is the collision intensity. And you can see that peaks just about 10 billion years ago. So here's present day. And so the universe was much smaller then. There was just a lot of collisions, but there's still quite a few collisions now. Okay. And now we talked about spiral galaxies and elliptical galaxies. We didn't talk about where elliptical and spiral galaxies form. Now you saw with those simulations that spiral galaxies seem to just form naturally out of collisions of all of these galaxies. Where do elliptical galaxies come from? And one current theory, and I think it's the best theory, is that when you have two spiral galaxies whose angular momentum is anti-correlated, in other words, you got one that's spinning this way and the other one that's spinning this way, when they combine and they lose virtually all of their angular momentum, then they no longer will have that spiral structure. And you just get this collision where it stops spinning. And when that happens, all of the gas and dust collides very quickly, produces a burst of star formation, eats up all of the gas and dust, and then then you really don't have any circling around of gas. You don't have any way to mix anything that's left. Star formation dies, and it turns into a nice red elliptical galaxy. And remember, elliptical galaxies are relatively rare. Most of the galaxies in the universe are spiral galaxies or irregular galaxies. And so the fact that this collision of galaxies where you kill all the angular momentum is relatively rare, kind of matches this theory. Okay. Also, when you have galaxies that collide, what you're going to see is remnants of these collisions that I'll show you in some videos shortly, and we call those tidal streams. So you can see some of those tidal streams here. And those tidal streams we can observe around our galaxy. So here, these colored lines represent observations of streams of stars that do not belong to the Milky Way galaxy. These streams of stars surround the Milky Way galaxy, and we believe those are the remnants of collisions in the Milky Way galaxy with other galaxies. And as you can see, there's dozens of them. So, this was a brutal time. Galaxies were colliding all the time. And the blue here has been exaggerated to show star formation. So the collision collapse really puts shockwaves through the gas and dust in the galaxy and really produces this burst of star formation. We call them starburst galaxies. And you can see it collided and then separated, and now it's collided again. And now in this case, we get essentially an elliptical galaxy where a lot of the gas and dust has collided, formed the stars, and then there's no gas and dust left over. And here is pictures of galaxies colliding, okay, all over the place. And the next video I'm going to show you is really powerful. What you're going to see is a simulation of colliding galaxies, and then at various points in the collision, we're going to compare the simulation to pictures of real galaxies colliding. So a simulation of two galaxies colliding. There's a picture of a real pair of galaxies colliding. And you can see now the galaxies are being warped. And that maps to another image we have of galaxies colliding. Now the galaxies are being ripped apart. And that maps this picture. And you can see the tidal streams there. okay, that are typically formed whenever two galaxies collide. I mean, it's just amazing. So I'll leave you with the fact that the Andromeda Galaxy has our number. In 4 billion years, it will collide with the Milky Way galaxy. And this is the way it appears now. There's the Andromeda Galaxy. In 2 billion years, it's going to be quite a bit larger. So if you're around, this is what it looks like. In 3.75 billion years, it will completely dominate the night sky. 3.85 years, what's going to happen is the gas and dust in the Andromeda Galaxy will start colliding with the gas and dust in the Milky Way galaxy, and we're going to see this burst of star formation and these glowing, these are not stars, these are the emission nebula that we talked about before. 3.9 billion years is going to look like that, and 4 billion years, it's just going to be a completely different night sky. And this is what it would look like in 5 billion years. The sky would be incredibly bright. And so that's as much as we have time for today. I'm open for questions. You feel free to turn on your mic. Brody asks, how much have quantum computers aided astronomy and cosmology? So Brody, actually, it's a good question. I'm working with a team in senior design class on that. The answer is 0. So quantum computers, to my knowledge, haven't actually done any practical calculation yet. They've done some test calculations, but these test calculations could have been done much faster with a classical computer. So I don't think quantum computers really exist yet on a significant scale. Yes, Art, it depends on what you mean by quantum computers. Certainly there's probably a dozen quantum computers in the world right now. The question is, does there exist a practical quantum computer that is doing practical calculations? The answer is 0. Okay. Why is the little cross formed when you take a picture of a bright star? So Joseph, good question. That little crosshair forms because there's the light reflects from various things that's inside your camera or inside the telescope. And so it really has nothing to do with the star itself and everything to do with the optical process. And you can even see this with your naked eye, because your naked eye is essentially a camera, and the eye as a camera isn't terribly sophisticated either. And so you will see, glows around bright object, and those glows are not caused by the object themselves. They're caused by the imperfections in your cornea, imperfections in the vitreous fluid inside your eye. So that's it. Other questions? Do not forget the exam. Don't forget that we have a participation score. Most of you have hit the 5 lectures limit, but not all of you. So exam is next Thursday night. That's correct. Well, not yeah. The exam is next Thursday, right? Yes. Did you hear that Betelgeuse was discovered to be 20% closer than originally thought? Yeah, Frank, I saw that news article. That's interesting. And that brings us up to only about 500 light years versus 700 light years. Yeah, thankfully that's still far enough away that it's no danger to us, but it does mean that when Betelgeuse goes supernova, it's going to be incredibly spectacular, much brighter than the moon. And my gosh, imagine if that happens in our lifetime. Other questions? Let's I went to see that on Halley's Comet. Yeah, I actually saw Halley's Comet in 1985-ish, was it? And the next total eclipse. Well, you definitely can see the next total eclipse. That's only in 2024. I went stargazing last week at the Outer Banks and saw, wow, you saw the Milky Way galaxy in the Outer Banks. That's impressive. That would be really nice. When is the 5-minute project due? Yeah, so Frank, let me put it on the syllabus. It's due November 12th. Actually, I think it's on the latest edition of the syllabus. I need to upload that. So I will be showing the project on November 17th. I'd like to have the 5-minute videos in November 12th. So that will give me time to select the best ones to show on the 17th. But good point. I will put that on the syllabus. Other questions? I'll answer anything. Might not be the right answer, but I'll answer it. Dog or cat guy? Definitely dog guy. Sorry. No question. Let me bring up a picture. Okay, so search dog. Okay. Okay, so this is, that's Cosmo down there, and that's Astro up there. So Astro there, Cosmo there. Cosmo's part Beagle, part Boston, and just loves to sleep. Astro is Jack Russell, who is just kind of he's cute, but boy, he's high energy. Always bouncing, always barking. How old are they? They're both about 12 years old. And this picture, so anyway, I try and keep them away from the mic. Other questions? Well, thank you so much. Have a nice weekend. Be sure to vote, no matter what else you do. And I'll see you on Tuesday. And of course, the exam is on Thursday. Thanks, guys. Do small galaxies have black holes at the center, or are they just basically big star clusters? So, Sam, I think I believe that all spiral galaxies and all elliptical galaxies have black holes at the center. I think that's the current party line. Irregular galaxies, I don't know. My guess is some do, some don't. But good question. I'll look that up. You always have good questions. Okay. Bye-bye, guys.